very good evening, everyone. Welcome to the series of M.Tech, the Great Amrita Alumni Conclave. Students are all optimistic about their future. Once that students has achieved a great height, we are proud of him or her to enlighten us about their knowledge. Well, today we have the topic that is VLSI Design in glance. We have the speaker Yadukrishnan, who will explain about the topic. He is working with AMD Design Engineer in AMD Design as an engineer, as a silicon design engineer. He is an Amrita Alumni of 2021 who has pursued M.Tech in VLSI Design from Amrita Vishwa Vidyapeetham. So before getting into the session, if any of your participants have queries, please type it in the chat box. So Yadukrishnan, I welcome you to the session. Therefore, we can start the series. Over to you right now.
Yeah, thank you so much for this warm welcome. Good evening, everyone. I hope I'm audible and I'm visible here. Can anyone give me an acknowledgement about that? Am I audible? Hello?
Yes, you are audible. You are audible.
Sure. Good evening, everyone. As mentioned in the introduction, my name is Yadukrishnan Gopinathan. I am an alumnus of Amrita Vishwa Vidyapeetham. I completed my M.Tech from Amrita Vishwa Vidyapeetham, Coimbatore. And currently, I am working as a silicon design engineer at AMD. So I would like to share some certain pointers about what VLSI design is. This can be useful for both B.Tech as well as M.Tech students who are planning to opt this particular genre or this particular area of interest. So basically, VLSI is an acronym for very large scale integration. So basically, whatever we are seeing inside a computer, be it an embedded system or inside the smartphones, TVs, or in our day-to-day lives, most of them are controlled by something which is manufactured through a process called as VLSI design. So if you imagine, like 10 years back, we had this big desktop PCs, which used to sit in our home. We cannot take this anywhere else. It used to be there in our home, and the laptops which were present then, it used to be very bulky. So from that stage to what we have is an Android phone, which is easily portable, and it has all the features and many more features that are not even present in personal computers. So from that stage to this stage, if we are checking, we can see that a tremendous reduction in the size has happened. So that is basically what VLSI means. So we are trying to integrate more and more on a very small area. So basically VLSI means we are trying to, whatever we are designing is basically called as a transistor. So the transistor amount or the number of transistors present inside the design is increasing rapidly. So previously, if you are taking the case of the oldest computer, it will have say hundreds or basically thousands of transistors. So that's why it was bulky. So on each of the chip, 100 transistors will be implemented. So like that, we will require say 10 or 20 chips. So like that, it was huge, right? So after that, coming drastically down, each single chip consists of billions of transistors. So that's why VLSI, the term came to existence. That is very large scale integration. So we are integrating more and more on a small area. So how was VLSI coming into a VLSI design? So basically, whatever we are doing, say if you are trying to paint, we require a basic idea. So similarly, VLSI also, if you want to design something, if you want a processor, we should have an idea about what that processor does or what all activities a processor should do. So all these things and how it should be designed, how it should be programmed, how it can be integrated onto a hardware, all these things, all these processes are collectively called as VLSI design. So the process of manufacturing any chip is called as VLSI design. So this particular activity is nowadays taught widely in every universities around the world. So it is basically a very niche niche technology that everybody can get interested in. So VLSI design basically focuses on two major domains, that is analog and digital. So analog means basically it comes to the area of sound, basically analog, mixing, mastering that sound, basically whatever related to sound, as well as in the case of hardwares, if you're going into a continuous signal, say a sine wave or something else, a continuous domain, that particular thing comes under analog, and then comes digital. So whatever processors, that is ICs, that you are using inside your laptop basically goes through the digital design flow. So basically I would be focusing more on digital design flow because I am working in that particular domain. So I hope all of you know what an IC or a chip is. So an integrated circuit or a chip is something that is present inside any smartphone, laptop, or be any smart devices that is available today. So such a device, that is such a system or a circuit, it requires a complex process of manufacturing. So there is like certain aspects that we move through. So it starts with the specification, which will be given to us by our designers or certain clients. In the case of if you are taking the case of say Apple. Okay, Apple will give us the specs. We need this much speed, the process should be this much cores, like that. So that thing is called as the specification stage. So from the specification, it moves to the design. So the design is where we try to manually code and create the design. So that is the process where we convert the specification into something that we can visualize. So from the design stage, it moves into a stage called as verification. So the verification is where whatever we have designed is working properly or not. We are going to check that. So after verification, then comes the stage called as testing. So the testing is where whatever we have verified and whatever we have designed, we will convert it into a different stage. So I'm not going much into the depth about what it is. It will be a lot of technical jargons. So I'll not be covering what that exactly terms are. So I'll just cover it on an overall basis. So design, then we have the verified design. So the verified design moves into a process called as testing. So the testing is where we try to, check whether if this design we are going into a manufacturing stage, whether there will be a defect, or what if a defect occurs, how that defect can be captured and how it can be eliminated. So this process is called as the testing. So after the testing, whatever the design is there, we are freezing that. So once we freeze that design, it is logged. Whatever the specifications they have mentioned, we have met that, we have designed that, we have verified that. After the specification is logged, we are trying to now implement that. So before implementing, we need to see like what are the devices. So basically everybody might be knowing about this logical operations like AND or XOR, all these gates, right? So these gates we will place it. Suppose it's an A plus B operation, so we will try to replace it with an or an XOR depending upon the functionality. So we will just convert whatever physical thing is present, I mean whatever the behavior is of the design that we have designed, we will just convert it into a physical implementation. So from the physical implementation, we will try to place those things. So each of these gates should be replaced by a transistor level design. So this will be then going into a fabrication process. So this is the entire outline of the VLSI design process. So basically, what is the impact of, or what is the necessity of such a process, complex process? You can just directly go and implement it. No, it's not like that. Conversion of a single idea into a design is it can be called as a pretty hectic process. So we need to understand and carefully grasp what the requirement is and then move step by step, because if any of this step which I have mentioned is eliminated, the entire process fails. So we have something called as pre-silicon and post-silicon, because whatever we are designing or implementing is implemented on silicon wafers. So that's why it is called as pre-silicon and post-silicon. So the design, verification, testing all happens pre-silicon, and on the post-silicon, the placement, or as I have mentioned, the physical implementation, then validation, all this comes post-silicon. So all these are the certain industrial aspects that we cover inside a VLSI design. So all these processes are very important, as I have mentioned. Why this is because if any one thing fails, it leads to huge loss in terms of industries. Because each of this, if you are manufacturing a single IC or a single die, it costs a lot for manufacturing just a single die. So the industries, what they go is they go for bulk manufacturing. So instead of manufacturing a single die, they manufacture say 100,000 dies, and they will be selling that, commercializing that, because that is much more feasible. Some industries have the required fabrication processes, some industries doesn't have the fabrication process. For example, Samsung have their own foundry, and similarly, Intel also has their own foundries, but AMD doesn't have a foundry. It has to depend on a third-party foundry. So if that is the case, then they have to pay a huge chunk of money for them just to manufacture this. And if that manufactured IC is failing, it leads to a huge loss. So that's why we have to follow this process. So whenever a person is opting for electronics and communication engineering, or a person is opting for electrical and electronics, or a person is opting for a master's course like VLSI design or embedded systems, they think that it's, even when I opted it, I thought it's a simple process. It's not. It's a complex process, because each process has its own importance. It's not that, okay, you are a designer, you have the prominent role. No, it's not like that. Each of these roles have its own role, its own importance. So if one is eliminated, it entirely disrupts the balance and it leads to total loss. So basically, what I have mentioned till now is just an outline about VLSI design. So why VLSI design is nowadays needed? So people are moving in a fast pace. Everybody requires things at the touch of a button. So if you want things to be done in such a manner, we require integration to happen more and more. Like right now, the integrated transistor count is around 1 billion. So we need, next moving forward, it will be 2 billion. It will be 3 billion. So according to that, Gordon Moore proposed that number of transistors within a design will multiply. Like it will be like it will multiply 18 times over 3 years, or a span of 3 years. So that count is actually going to be extinct, because the time he proposed that till now, the count has been increasing drastically. Right now, as I have mentioned, some processors even have 10 billion to 20 billion, 100 billion, 154 billion transistors are integrated on it. So if that is the case, then Moore's law is actually extinct, right? If you can think of that, it is going into an infinite level. So if that is the case, then what is next? So that is where designers like us come into picture. So we have to, design the aspects in such a manner that whatever requirement is there, it is met, as well as whatever requirement from the customer side, that is we who requires the smartphone, or whoever want things to be done at the touch of a button, their requirement is also met. At the same time, all that requirements is met at the expense of minimal resources. So this is what we as a designer, or we as an engineer, does in these industries. So as I have mentioned, I have been working in AMD for the past for the past 2 years, and I have been I have been doing my internship, and post that I got an FTE from there. So till now, what I have been doing is I have been doing testing as well as verification. So all these processes are pretty complex. So what is the scope of choosing such a VLSI design, or what will you learn if you take this course of VLSI design? So VLSI design have different verticals, as I have mentioned. It has the process of design, it has the process of verification, it has process of testing. So apart from this, what are the things that you will be focusing more on? So there is something called as a digital system design, which is the like the most core, or the most very important course which is being taught these days. So the digital system design textbooks are the Bible for any VLSI design engineers. So this particular course gives us an insight on how to design a digital system, or how to design a given system for meeting a given requirement. So this is the particular course which we will be constantly learning and constantly revising throughout the entire if you are interested in VLSI design, you will be constantly doing this particular course. Then there will be courses on which will be taught, like digital IC design, analog IC design. Then there will be courses taught on STA. The one of the most premier, most attractive thing that I found in Amrita is most of the courses that is being taught here on VLSI design is pretty much industrial oriented. So whatever the courses that we are learning can be applied much to the industry. For example, static timing analysis is a very niche course that is offered at Amrita. So this comes as an elective, but it is the crux, or the major important part in a digital design engineer's life. So if you are designing a given circuit, say you have an input and it has to come out at the output. What if the input is coming at the output after 100 nanoseconds or 100 seconds? You are inputting, say, 1 plus 1 at the when you press the equal to sign, you are getting 2 within what, like milliseconds, right? What if that doesn't happen? What if it waits for like 10-20 minutes and it is giving out the result? Then there is something wrong, right? You don't want to have a calculator like that. So the purpose of a timing analyzing or a timing engineer or a static timing engineer is to understand or to check whether the inputs that you have given is meeting the timing requirements. That is, whether the process is happening according to the timing requirements that is needed, and we are getting the results as expected. So the static timing analysis is a course which gives you an idea about how to meet the timing requirements, and that is being taught at Amrita, which is absolutely fantastic because that is something that is very much required. So this course is very much important in the perspective of VLSI design. Then there are courses on design aspects, like as I have mentioned, digital IC design, which gives on how to convert this whatever design that we have implemented as a code into a physical implementation, how that is happening. All these are being taught very much and in a well efficient manner at Amrita. The only thing that we have to focus is enhancing our knowledge base that is based on the current industrial trends. So even though all the courses are taught, we should be also aware about what is happening in today's industry. What is the new processor that is being released? What is the speed, or what is the processor that is present in your phone? Most of the people they will say like, okay, this is a Snapdragon phone, but what is the feature? Okay, Snapdragon released a 600 version, and then Snapdragon is releasing a 700 version. What is the difference between those things? If we are thinking from that perspective, then this particular course will be very, very interesting for you guys. Then what is the relevance, or what is the scope of this course in the industrial perspective? As I have mentioned, there are like different verticals for the VLSI design. So if there are like design rules where you will be getting the specifications, you will have to code it, you will have to implement the design. So that is where design engineers are present. Then there comes verification rules. Then there is like testing rules. So majority of the industry in today's world are hiring engineers who have opted for VLSI. There are companies like Google, AMD, Intel, Apple, then Texas Instruments, Analog Devices Inc., which all are top VLSI firms which recruit, and they are looking for engineers who are prominent in VLSI designs. And most of these companies which I have mentioned are visiting Amrita. I'm fortunate enough to be, and very happy to say that I got placed in AMD because I have opted a VLSI design course in Amrita, and the design course was pretty much structured, and I am pretty much happy at the place where I am. So if we are opting, like people say that, okay, there is recession happening, we shouldn't be focusing, like, no, there is nothing like that. Everywhere there is requirements are there for engineers. If you get an internship, well and good. If you are not getting internship, don't worry, you will get it sooner or later, or you will have more and more opportunities. The faculties in Amrita, the placement cell, everybody tries their best to get to grab the attention of the recruiters and bring them in, and also to help us out in this particular verticals. And whatever is being offered, it is being offered for everyone else. So there is no you don't have to be worried about whether you have opted for VLSI design and whether you will get a job. No, there is a guarantee that you will get a job. So that's pretty much it. This is what VLSI design is, then what you learn in VLSI design, and how Amrita plays a vital role in modeling your career in terms of VLSI design. And I'm just speaking about VLSI design. There are other branches as well, but in terms of VLSI design, I can give a bit more clarity and a bit more perspective. And what are the current industrial trends? So there are roles for design engineers, then there are roles for physical design engineers, then there are roles for design verification engineers, and I'll just explain about what each of these people do. So the design engineer, the purpose of a design engineer is to take the specification, understand the specification, and they will write something called as an RTL, or it is called as the register transfer layer, or the it is the place where we convert the specification into a model, which is called as a behavioral model, which will kind of give the behavior of the given system. You can say it like that. So the purpose of a design engineer is to design or model the specification into a behavior. The next role is called as a design verification engineer. So the design verification engineer's job is to point out that whatever the designer has done is wrong. So the design engineer works in that perspective. So what he does is he creates a reference based on the specification himself, and he compares the designer, whatever the designer has done, he compares it with the reference that he has created, and he tries to find any issues or he tries to find any bugs. So that the purpose of the design verification engineer is to verify the design or to verify the functionality of the design. Then comes the testing engineer, or also called as the design for testability engineer. So the DFT engineer, what he does is he adds some extra logic into this design, and he makes the design more controllable and more observable. So why we need more controllable and more observable design is because we need to see if what if this design goes into a fabrication. Whatever we are designing is actually as a code, right? So what if we are fabricating it and due to some manufacturing defects, what if something goes wrong? So he will forecast this and he will try to ensure steps to mitigate this. So that is the role of a testing engineer. Then comes the physical design engineer. The purpose of the physical design engineer is he will convert this behavioral model into a physical implementation or into a more hardware perspective. So the purpose of the physical design engineer is to do the layouts. He will create all the blocks. He will change the behavior into a logic, or he will convert basically A plus B, as I have mentioned, A plus B. He will convert it into an or an XOR gate depending on the requirement. Then there are some other engineers like as I mentioned, static timing analysis engineer. So ST engineers, what they do is they check whether the timing requirements are met. Then there are engineers for power and area analysis. So they will check whether, okay, if we are keeping this particular transistor here, whether it will consume more area, whether we are keeping two transistors looped together, whether it will consume more area, or whether the area requirements are met, or whether we require more area. All these things are analyzed by these engineers. And also there are engineers for checking the power. You might have observed, right? Your phone, after a long time, it is getting heated up. So all these are due to some certain defects that might have come. Any designs might, over the time, it will deteriorate. Whatever be it, it is not for lifelong, right? It will automatically deteriorate. So the power engineers, they try to ensure that whatever design that we are implementing has long life. So that is a different role. Then there are other different engineers. All these things can be implemented like small chunks. Like a big design will be implemented in a small chunk. They will take one particular model and will be giving to one particular team. They will be taking a different model, giving to a different team. So there are like different roles for that as well. So as I have mentioned, these are the different roles, and these are the areas where people who are opting for VLSI design or those who are doing their bachelor's can try. If they are interested in VLSI design, they can also try to get jobs in these verticals. So these are the current industrial trends or the current industrial roles that are being called for. And also the industrial trends include the size, the feature size. What is the smallest size of a device that is being used? So for example, 5 nanometer. Apple built their iPhone chips, that is the bionic chips in 5 nanometer. So all these are the industrial relevant newses that you can get. So you try getting updated with these newses. Prepare yourself, master yourself in the digital design courses, take courses, take your lectures help, do assignments, all these things. It will give you a smooth onboarding to your upcoming careers. And I hope that most of you who are listening to this will be interested in pursuing this career in this particular domain, as well as they will get a beautiful life ahead in Amrita, as well as further in their career as well. Yeah. Thank you so much.
Hello.
Yeah, hi.
Am I visible? Yeah.
Yeah.
Well, thank you. Thank you, Yaduji, for that was a beautiful section.
Thank you so
much. So far our participants don't have much of a questions to be asked. So thank you so much.
Yeah, thank you
so
much.
Nice.
Thank you, everyone. Yeah, have a great day.